Hi everyone, this is Mrs. J, and today we're going to talk about characteristics of functions as well as how to graph linear and absolute value functions. I have a quick warm up for you guys, so please pause the video and hit play when you're ready to check. Okay, go ahead and check your work. So part A, we have a linear equation that requires you to distribute, combine like terms, and then finish solving using subtraction and then division, and make sure you simplify your final answer. And then in part B, we have an absolute value equation. So remember, for this, we try to isolate our absolute value term. And then we actually have to make two separate equations, one where the absolute value is equal to the positive version of the constant and then the negative version of the constant. So here we have two answers. So before we start talking about the characteristics of functions, it's super important that we understand what a function is and the mathematical definition of a function. So a function is a relation where every input has exactly one output. That exactly one is super, super important. So every x has only one y. So let's look at a couple different representations of functions and non-functions. So if you look at this first relation, I plug in 4, I get 12. I plug in 5, I get 15. So every individual x value only has one y value. But if you look at this next relation, here I plug in 4 and I get 12. But then here I plug in 4 and I get 15. So this x value of 4 has two different y values, so it is not a function. And you could see here is another scenario that would make this not a function. I plug in 5 and sometimes I get 18, sometimes I get 21. So here this x value or this input has two different outputs, making it not a function. Graphically, we can test for a function using what's called the vertical line test. Where essentially if you drew a vertical line at any point on your graph, your line should only cross the vertical line at one point. So here you can see if I moved this vertical line left to right, it would only touch my graph at one point at any given time, meaning every x value only has one y value. But if you look at this graph, if you lay a vertical line here, the graph is touching twice. So that is telling us that this input has more than one output, making it not a function. So if a graph fails that vertical line test, it is not a function. So now that we have reviewed the mathematical definition of a function, we're going to start off by talking about how to define the domain and range of our functions. So the domain is the set of all possible inputs or x values that work for our function, and the range is the set of all possible y values or outputs that work for our function. We're going to define our domain and range with a couple different notations. We'll use these notations for other characteristics as well, but we'll review interval notation, which uses parentheses and brackets to show max and mins. So if you use parentheses, it means that the values are excluded. So we don't want to include them in the domain or range. And if you use brackets, it means that those values are included. So we would like to include them in our domain and or range. We will also use inequality notation. So we'll use the less than or equal to, greater than equal to, or this all real numbers symbol. Really, it's written more like this. Both of these are pretty common notations. This last one, it's called set builder notation or just set notation sometimes. It's essentially inequality notation with some extra fancy braces along the side as well as defining your variable. So we read this as x such that x is greater than 1 or y such that y is less than or equal to 2. We won't be using that in this lesson, but I just want you to have seen it or be aware that this is a notation that exists. It's just not as common. All right, let's give one of these a try together. So here we're going to define the domain and range in interval notation. So let's look at this first graph. Arrows on the end of a graph mean that it's going to continue heading in that direction forever. So if I look here, I see an arrow, which means my graph will keep heading down and to the right forever. And here, this means my graph will head up and to the left forever. So for this graph, if I'm defining the domain, since it's going to the right forever and to the left forever, it the domain is going to be all real numbers. The way you show that with interval notation is you do negative infinity, which is our lower boundary, and then you do a comma, and you do positive infinity. You can put a plus sign in front or not. Either way means the same thing. And with infinity, we always use parentheses. We don't include infinity because infinity is not an actual number, so we can't include it. So parentheses always go with infinity. Now, if we're doing inequality notation, we would say x equals all real numbers, so that fancy symbol for all real numbers. For the range, again, this graph is going to go down and up forever, so it's eventually going to cross every y value, so our range is also all real numbers, negative infinity to positive infinity, and we can say y equals all real numbers. So it's very common for different types of functions to have domains and ranges that are all real numbers. Now here you can see we have a graph, but it has endpoints. So it will have a restricted domain and range. So again, for the domain, we're looking at all the x values that it covers. So I can see that it covers from here to here. I'm just looking at the numbers on my x-axis only. So with interval notation, let's start on our smallest boundary. So I see the smallest boundary is -3. And I see that my upper boundary is +1. And now here, I see that I have this open circle that's called an open coordinate, and it means that that point is not included. So for -3, we need to have a parenthesis there. But if you look here at this endpoint, it is a closed interval, it's colored in, and closed intervals are inclusive, meaning we want to include the value. So we have -3 to 1. Now with inequality notation, if you are bounded between two numbers like you are here, you're actually going to smush x in between those two numbers. So we have -3, and then here, since -3 is not included, I'm just going to say is less than x, but here 1 again is included, so I'll say is less than or equal to 1. So this is a way of showing that it's between -3 and 1. Now for our range is all of the y values that our graph touches. So I can see it's going from -4 to 0. So again, our low boundary is -4, and I can see it is part of our graph, so I'm going to include it. Our upper boundary is 0. Although it's not included here, as long as your graph touches it somewhere, we will include it. So both of those are inclusive. They are brackets. And then for our inequality notation, again, it's smushed between two numbers. So we're going to say -4 is less than or equal to y. Make sure you're using y for the range, is less than or equal to 0. And there you have it. Okay, go ahead and pause the video and see if you can give this one a try on your own. All right, go ahead and check. So this graph has an endpoint on one side and an arrow on the other. So this graph is going to go left and up forever. So our left boundary for x is actually -infinity. And you can see our upper boundary is +1. We're going to include that because it is a closed coordinate. Now for my y values, I see my lower boundary is 0 and my upper boundary is +infinity because it goes up forever. And remember, infinity always has a parenthesis, and I would like to include 0 with that bracket. And then here for inequality, you'll see that it's just all the values less than 1 or equal to. So x is less than or equal to 1, and then y is greater than or equal to 0. All right, so now we're going to move on to a new characteristic that we're going to practice describing, which is intervals of increasing and decreasing for our function. So a function is increasing when the slope of our graph is positive. We know that the slope is positive if you trace your graph, and we always trace our graph from left to right, just like you read a book. If you're tracing your graph and your pencil is going up, we have a positive slope and our graph is increasing. Now, if you trace your graph and your pencil is going down, we have a negative slope, meaning our graph is decreasing. So here I'm increasing, and then I'm decreasing, and then I'm increasing. Now, when we describe intervals of increasing or decreasing, we describe it as the x values where that's happening. So it can get a little tricky because we're not actually describing how high or how low it goes. We're just describing where it is going up and where it is going down. Another thing I'd like to point out is, depending on which textbook you're working with, some textbooks include the turning point in both increasing and decreasing. Some do not. So I will not be including turning points. Technically, when you are turning or when you're changing from increasing to decreasing, you are neither. Your slope is 0 for that instantaneous moment. So I'm not going to include it. So you'll see that I will only use parentheses when I'm doing this, but some textbooks will use brackets for those turning points. All right, let's give this one a try together. We're going to determine the intervals of increasing and decreasing in both interval and inequality notation. So for increasing, again, it's where my graph has a positive slope. So if I trace my graph, my pencil's moving up. So I can see that that is happening in this region. But again, we don't want to describe it in terms of the y values. We always describe this in terms of the x values. So I see that that's happening from -2 to 0. Okay, that's where my graph is increasing from x equals -2, and again, I'm not going to include the turning points, to 0. And with inequality notation, that'd be -2 is less than x is less than 0. Now I see that my graph is decreasing in 2 different points, here and here, because if I trace my graph, my pencil would be going down. But again, I want to describe it in terms of the x values where that's happening. And I'm also going to exclude endpoints. I will not include endpoints in increasing or decreasing. So this is happening from x equals -3 to x equals -2. Now here we actually have that second interval. So you can actually separate the intervals with what's called a union symbol. So it means, unions just mean this or that. So we'll use a union symbol, or sometimes you'll see commas as well, but I'll use a union symbol. And then for this next segment, it's decreasing from x equals 0 to x equals +1. So again, it's always in terms of the x values. And then for inequality notation, it's between -3 and -2. And I'll do a little comma for this one. And then between 0 and 1. So there you go. So again, the tricky thing is remembering we describe these intervals in terms of the x values where they are happening. All right, here's one for you to try on your own. So go ahead and pause the video and give it a shot. All right, go ahead and check. I can see that my graph is increasing right here, which is from x equals -4 to -2. And I can see it's also increasing here, so from x equals 2 to x equals 4. Then I can see my graph is decreasing from here from -2 to +2. So the last main characteristic we're going to talk about today is what's called the end behavior. So the end behavior is the way your graph behaves as x increases or decreases without bound. So what that means is our graph is getting, as x is getting really, really, really large or really, really, really small. So it essentially means moving way to the right or way to the left. So with end behavior, your graph can go up forever, which means it would approach positive infinity. Your graph can go down forever, which means that it can approach negative infinity, or your graph could actually approach a value. And please note that if your graph has an endpoint rather than an arrow at the end, it technically does not have end behavior on that side. So you could just write no end behavior. Now here's the way that we're going to write and read these end behaviors. It is important that you both read and write them correctly. So here, this says as x approaches positive infinity. Again, the plus sign is optional for positive infinity. So as x approaches positive infinity, which means to the right, f of x approaches blank, and this is what you fill in. And I would like you guys to use f of x rather than y, just to practice that function notation. So again, this just means going to the right, my y values are approaching what? Are they going up, are they going down, or are they approaching a value? And then to describe the end behavior on the left, it says x approaches negative infinity, f of x approaches blank, and this is what you will fill in depending on your graph. All right, let's give these a try together. So let's start with our end behavior on the right. So I'll start by writing as x approaches positive infinity, f of x approaches, and I'm going to look at my graph. So if I look off to the right, I have this arrow implying that my graph is going to keep heading to the right and down forever. So I can see that to the right, my graph will actually go down. So my y value, or f of x, will approach negative infinity. And then on the left side, as x approaches negative infinity, which just means moving to the left, I can see that I have the arrow that's pointing up. So that means that f of x will approach positive infinity. So it's okay for the end behaviors to be different. It's also okay for the end behaviors to be the same. Maybe both sides go up or both sides go down. Now let's look at part B. Here we have what's called a horizontal asymptote. So you can see that our graph is actually approaching that value. So here, end behavior will actually be a value instead of positive or negative infinity. So here, as x approaches positive infinity, f of x approaches, so you can see that the y value is approaching 5. And we actually have the same end behavior on the left. So as x approaches negative infinity, f of x approaches 5. It's okay to approach a value on one side and then to go up or down on the other. It's okay for one side to have no end behavior and the other side to have end behavior. So any combination of these is completely fine. All right, go ahead and pause the video and give these two a try on your own. All right, go ahead and check here. So this first one we could see as x approaches positive infinity, f of x approaches positive infinity. So moving to the right, my graph goes up. And as x approaches negative infinity, f of x approaches negative infinity. So moving to the left, my graph goes down. You can see for part B, both sides go up. So here I described the two end behaviors separately. As x approaches positive infinity and as x approaches negative infinity. However, this is optional. If you notice that the end behaviors are the same, you can write it all in one. You can say as x approaches positive or negative infinity, f of x approaches positive infinity. So again, this is completely optional and it means the same thing as writing them separate. It's up to you which one you choose to do. All right, so now we're going to move on to some graphing. So today we're going to be graphing constant functions, and then a little more broadly, linear functions, and then absolute value functions. So we're always going to start by looking at what's called a parent function. So a parent function is kind of the most basic form of that function. So if you ever have a function that looks like this, f of x equals c, where c is a constant, just meaning a real number. So if you have f of x equals 5 or y equals -2, that is what we call a constant function. Constant functions are horizontal lines at that y value. So you'll see that the function, the actual equation, does not have an x in it. And again, that just makes a horizontal line wherever that constant is, whatever that y value is. So our domain for these types of functions is always going to be all real numbers, but you can see that our range is restricted to whatever that c value is. So we can do little braces and just write whatever that c value is, or you could just say y equals c to define the y values of your range. So key features, again, these make horizontal lines, meaning the slope is 0. And so maybe you're wondering, okay, this is when it says y equals a constant. Well, what about if you have x equals a constant? Why aren't we talking about that? Well, if you have x equals a constant, it actually makes a vertical line at whatever that x value is. And since it's a vertical line, it physically fails the vertical line test. So it's not technically a function, it's still a line. We will still be working with those types of lines this year, but today we're only going to be graphing functions, so we'll only see y equals a constant. But again, you should know how to graph x equals a constant as well. So for our linear functions, more broadly, the parent function looks like this. Y, or f of x, equals x. So this is a graph of y equals x. So you can see our domain and range are both all real numbers, negative infinity to infinity. So you should see this for any linear function. Some key features: it does always make a straight line for the graph. And you'll notice that since it's a straight line, the rate of change is constant. So these graphs have a constant slope. Sometimes the slope is positive, sometimes the slope is negative, or sometimes the slope is 0 and it becomes a constant function, but the slope is always the same. Now there's a few different forms you might see this in. You might see this in slope-intercept form, y equals mx plus b, where m is the slope and b is the y-intercept. So hopefully that looks familiar. Or you might also see this in standard form, ax plus by equals c. So we'll work with some in this form as well. From this form, you could either rewrite it in slope-intercept form, which is really nice for graphing, or you can use this form to actually help you find the x and y intercepts and graph from there. Really, you only need 2 points to graph a linear function, because if you have those 2 points, all you need to do is connect them to make a straight line. All right, let's try graphing one of these together. So here we have an equation in slope-intercept form. So I'm going to leave it in this equation to graph. So here, y equals 2x minus 5. I can see that this is in y equals mx plus b. So I can see that my b value, which is my y-intercept, is negative 5. And I can see that my m value, which is my slope, is positive 2. Now, I like to write it sometimes as 2 over 1 because the slope, if you remember, the slope is rise over run, meaning vertical change over horizontal change. So sometimes when people just see a 2, they kind of panic and they're not quite sure what to do. But remember, 2 is just 2 over 1. So you go up 2 over 1. But when you're graphing, you should always start with the y-intercept because you need to have a starting point. And then from there, I will follow my slope. I will go up to right 1, and I will continue that pattern for as far as I can. And then I will do the opposite in the other direction. I will go down to left 1. And then once I have plenty of exact coordinates, I'm just going to connect my dots in a straight line and make sure you place arrows at the end of your graph. So now that we've graphed it, we can define the domain and range. Well, hopefully we know that since it's a linear function, both the domain and range should be all real numbers, always. And then we are going to find the x and y intercepts. We're going to do this algebraically. Even though we can sometimes see the x and y intercepts on our graph, I want to review how to do this algebraically. So to find an x-intercept, our strategy is going to set y equal to 0, because if it's crossing the x-axis, that means your y value is 0. So I'm going to go to my original equation, and I'm going to replace y with 0, and then I'm just going to solve for x. So I will add 5 to both sides and divide both sides by 2. X equals 5 over 2. So that's my x-intercept, which you can see matches what I see in my graph. And then for a y-intercept, the way you find a y-intercept is you set x equal to 0. So I'm going to substitute x with 0 in my equation. So 2 times 0 minus 5. And then I'm going to simplify and I get y equals negative 5, which we already knew was our y-intercept, but it's important to know how to do this algebraically as well as graphically. All right, let's try another one together. So you can see here that my equation is in that standard form that we talked about. So there's a couple different ways we can go about this. one way is we can actually graph this again by just finding the x and y intercepts and then connecting those in a straight line. So let's try doing that. Our x-intercept, remember we set y equal to 0. So 2x plus 3 times 0 equals 6. 2x equals 6, so x equals 3. So I can plot that over here on my graph. That's my x-intercept. And then let's find our y-intercept algebraically as well. So I'm going to replace x with 0. 2 times 0 plus 3y equals 6. 3y equals 6. Y equals 2. So that's my y-intercept. And then I could connect those dots to make a straight line, and there's my graph. Or if I want to do this maybe a little more accurately and get some additional coordinates, I could take my equation and rewrite it in that slope-intercept form. So I could start by subtracting 2x from both sides. So we get 3y equals negative 2x plus 6. And then I can divide both sides by 3. Make sure you're dividing every term on both sides. So you get y equals negative 2 over 3x plus 2. So you can see here that my slope is negative 2 over 3, and my y-intercept is 2, which we found earlier, so that's good. And if you look from here to here, I am going down 2 over 3 for my rise over run. Or I could do the opposite and going to the left, up 2, left 3, up 2, left 3. So I can continue my pattern to get a few more coordinates. So again, when your slope is negative, you go down and to the right rather than up and to the right. And then last thing we're going to do really quick, let's describe our domain and range, which we know should be all real numbers for both anytime we have a linear equation. So there you go. All right, go ahead and pause the video and give this one a try on your own. All right, go ahead and check your work. So here you can see that I kind of approached this in two different ways. I found the x and y intercepts, and you could just connect those, or you can rewrite it in that slope-intercept form. So it's really good to know both ways of doing it. The more ways you have of doing things in math, the more successful you will be. So make sure you're comfortable with both of these methods. All right, the last thing we're going to be doing today is graphing our absolute value functions. So again, we are going to start by looking at the parent function, which is just f of x equals absolute value of x. So this is what our parent function looks like. We could get this by making a table of values, plug in x equals 0, 1, 2, and get the y values. And remember, an absolute value is simply denoting the distance of that value to 0, and the distance is always positive, so it's essentially wiping out any negative. So the absolute value of negative 3 is 3. The absolute value of 2 is 2. So again, it helps you find the distance from that value to 0. So this is what our graph looks like. Again, it makes that kind of V-shaped graph. So you can see because the arrows go left and right forever, our domain is all real numbers, but our range for these graphs is going to be restricted. For the parent function, you could see that it's everything above and including 0. So 0 to infinity with a nice bracket for 0 to be inclusive. So there's different forms that you'll see, but we really like to graph from what I like to call vertex form, which looks like this: a times the absolute value of x minus h plus k. So when it's in this form, it's really easy to see the vertex, which is a defining feature of our graph. Our vertex is always going to be at h, k. Now, one thing you'll notice is that in this equation, it says x minus h, but in the vertex, it says positive h. So what you see in the equation and the x value you see in your vertex are always going to be opposites. But you'll see here that this says positive k and positive k. So for the y values, it's going to match. But just remember, for the x values, it's always going to be opposite. And then that a value out front is going to be the slope of your graph moving to the right. So a equals slope to the right, And what I mean by to the right is to the right of your vertex. So if your a value is 2, the slope of this piece will be 2. Now the slope of the line to the left of your vertex is just going to be the opposite. So if this slope is positive 1, this slope is going to be negative 1. Okay, so that's how we can graph these functions pretty quickly and easily. All right, let's try one of these together. So here it is in that nice vertex form. So I can look at it, and I'm always going to start by determining my vertex. So I can see that since it says x minus 2, the x value of my vertex is actually going to be positive 2. And I see my k value is positive 6, so my vertex is at 2, 6. Now I can see that my a value is negative 2. So that's going to be the slope of my line to the right of the vertex. So I start at my vertex, and I'm going to follow a slope of negative 2. So I go down 2 over 1, down 2 over 1. So I'm going to follow that pattern moving to the right. And then I'm going to do the opposite moving to the left. I'm going to go down to left 1, which actually creates a positive slope, everything to the left of my vertex. So if you look here, my slope is positive 2, and then here my slope is negative 2. We can also now define our domain and range. Remember, our domain should always be all real numbers for these, but our range will be restricted. So in this case, our low value is negative infinity because our graph is going down forever. And you can see that I do reach a maximum value at y equals 6, and that is included. So now we're going to find our x and y intercepts algebraically. So here we get a little extra practice for solving absolute value equations again. So let's start with our x-intercept. So for our x-intercept, again, we set y equal to 0 and we solve. And I know that sometimes we do see the intercepts clearly in our graph, but I really want to make sure you know how to do this algebraically. So first we need to isolate our absolute value. So I'm going to subtract 6 from both sides. And then I'm going to divide both sides by negative 2. And now I need to set up those two separate equations. X minus 2 equals positive 3. And then x minus 2 equals negative 3, and then I can finish solving. And then the nice thing when you have the graph is you can go back and confirm that those are correct. So it does match what we have in our graph. So that means we can feel pretty confident that our answers are correct. So I will box our answers. And then last, let's find our y-intercept algebraically. So again, for this, we set x equal to 0. So we have y equals negative 2 times the absolute value of 0 minus 2 plus 6. So we have negative 2 times the absolute value of negative 2. Now the absolute value of negative 2 is positive 2. And then we have negative 2 times positive 2. So y equals negative 4 plus 6. So y equals positive 2. Again, we can confirm that by looking at our graph. So we can feel pretty confident, again, that our y-intercept is correct. And there you have it. All right, let's try one more of these again together. This is our last example together. So our vertex, again, it's in that vertex form, a times the absolute value of x minus h plus k. Since this says positive 3, I know that the x value of my vertex will actually be opposite, so negative 3. The y value will always be the same, so positive 1. And then my a value is 2/3, which will be the slope to the right of my vertex. So I start at my vertex, again, negative 3, 1. And then I follow the slope of 2/3 to the right. So up 2, right 3, up 2, right 3, up 2, right 3. And then I'm going to do the opposite going to the left. So up 2, left 3, and it makes that nice V-shaped graph that is symmetrical over about the vertex. So these slopes will always be opposite. Again, our domain should always be all real numbers for absolute value functions, but our range should be restricted. I can see that our low value here is +1, but then it goes up forever, so it's 1 to infinity, and infinity is never included. Now let's do our x and y intercepts again algebraically. Let's find our x-intercept. So you might notice something. Our graph does not cross the x-axis, which is totally fine, but I want to show you what that looks like algebraically. So I'm going to start by subtracting -1, or subtracting 1 from both sides, and then I can multiply by 3 and divide by 2. So here's what I have. So we know that the job of absolute values is to take a value and essentially make it positive. So an absolute value expression by itself can never ever equal a negative number. So whenever you see that scenario, you know that there's no solution to this equation. So if there's no solution to the equation, that means that there's no x-intercepts for this graph, which again is totally fine. Some graphs will not cross the x-axis, and depending on the type of function, there are some functions that also will not cross the y-axis, so it just depends on your graph. And then let's find our y-intercept algebraically. So we're going to set x equal to 0, so 0 plus 3, and then plus 1. So y equals 2/3 times 3 plus 1. Y equals 2 plus 1. So we can see that our y-intercept is 3, which we can confirm by looking at our graph. All right, here's the last one for you to try on your own. So pause the video and give it a shot. All right, go ahead and check your work here. So remember, the x value of the vertex will always be opposite of what you see in the equation. So it should be at +4, -2. My slope going to the right is +1. My slope to the left is -1. Sorry, +1/2 and -1/2. Domain is all real numbers and range is 2 to infinity. And here you can see my algebraic work for finding the x-intercept, which is confirmed with my graph. And here's my algebraic work for finding the y-intercept. All right, that is all for today's video. Thank you so much for watching.